ago, um, we looked at finding the inverse of logarithm functions and exponential functions. We're now going to look at the graphs and how they compare. So we're going to do a quick review of inverses. So we need to fill out the chart x plus 1 squared minus 3. The fastest way to do that is on your calculator. So go to your calculator, type in that function. And then just go to table. We'll go back here, right there. All right. So -4, 6, -3, 1, -2, -2, -1, -3, -2, 1, and 6. So let's graph those points. -4, 6. Oh wait, that's not 4. Sorry. -4, 6. -3, 1. -2, -2. -1, -3. Oh, did I mess something up? No. 2, 6. Okay. So this quadratic looks like that. Essentially, what we did was we took the y equals x squared quadratic, and we moved it left 1, and then we moved it down 3. So we took the regular x squared, moved it left 1, and moved it down 3. What does it mean to take the inverse of a function? Switch what? We're switching the x's and y's. We're switching all of the x values and all of the y values. So for the inverse function of f, the domain is the old range, so the new range is the old domain. So it would be -4, -3, -2, -1, 0, 1, and 2. First off, is f of x... Oh, we'll get to that. Never mind. So now graph the inverse. -6, -4. Wait. Did I do that right? -6, -4. Oh, wait. It should be 6, huh? Sorry. That should be positive, and that should be positive. Okay. My mistake. I'll fix that for all future generations. So, 6, -4. That looks better. 1, -3. -2, -2. -3, -1, -2, 0, and then right here, and then right there. Okay. So that is the inverse of that parabola. So the first question, how would you describe the movement of the points in f of x to the points in f inverse of x? If Braden's making this little 90-degree rotation, is that what happened? I guess you might be able to describe this as a rotation, but you know, maybe in general that would work. I don't know. It's not usually how we talk about it, because it makes more sense to connect this point to that point. It's a reflection across what? The 45-degree line. So if I draw that dotted 45-degree line, this point became this point, and if you'll notice, it jumped straight across. That cuts the line in half. That 45-degree line cuts that jump line exactly in half. And that's true of all the points. If we connected those dots all over, that's what's going to happen on all of them. They all jump to the other side of that 45-degree line at a right angle equal distance. Okay, so the next question says, where do f of x and f inverse of x intersect? So there are two intersections, right? There's one here, and there's one here. What do you notice about those 2 points? Well, if you look at it in terms of inverse, if you take the point -2, -2, and flip it around, you still have -2, -2. The other way to look at it graphically is the only points that didn't move are the ones that are on this 45-degree line. Okay, so where do they intersect? On that 45-degree line. That's the only time those two graphs are going to intersect. Now, you might say, oh, they intersect right here, but do they really? Yeah. And sometimes it will look like an intersection, but it's not really an intersection because of how it rotated. So, and if you're a bad drawer. Okay, so why do they intersect on that line? What did Travis say? No. Well, what is it about being on that line that means that they didn't move? Okay, you could say it reflected a point about itself, which doesn't do anything, but numerically, why did they not move? The x and the y are the same values. That's why they don't move. Because x equals y, exactly. Well, so what is the equation of that 45-degree line? Y equals x. It has a slope of 1, and it has a y-intercept of 0, so it would be 1x plus 0. So this line is y equals x. So any point on that line has an x value that's equal to its y value, 1, 1, 2, 2, 3, 3, 4, 4, and so on. So any time that a graph hits that line, its inverse is also going to hit at that same spot. That's always going to happen. Okay, so let's find the equation for f inverse of x. How would we invert y equals x plus 1 squared minus 3? Well, you could go through, list all of the xy pairs, flip them, and list all the new xy pairs, but I don't have that kind of time. Just switch the x and y in the equation. So x equals y plus 1 squared minus 3. Now the trouble is it's not in function form, so we have to solve for y. So what would you do? So x plus 3, and then, well, equals, we're smart, so we're just going to skip some steps. So if I undo this, now what? You could, but the exponent is a number. It's not a variable. So take the square root. But anytime you square root a variable squared, you get plus or minus. So plus or minus the square root of x plus 3, and then you'll subtract 1, and we usually put that out front. So this is the inverse. -1 plus or minus the square root of x plus 3. So the next question says, are f of x and f inverse of x functions? F of x is. Why is f inverse not a function? Right, if we look at, my graph's getting kind of messy, but the green graph passes the vertical line test, but the blue graph fails almost everywhere it exists. It fails. And you can see that in the function. There are actually two functions. -1 plus the square root of x plus 3, which is the top half, and then -1 minus the square root of x plus 3, which is the bottom half. Okay, get rid of some of this stuff. Wish you could, huh? Okay, so find the domain for f of x. Where is f of x defined for its domain? All real numbers. So the domain is all real numbers. What's the range? So everything from here up, we have two ways to represent that. Either bracket -3 to infinity, which makes sense to me and you. That's the way they do it in calculus. Or the way that I think they did it on the SAGE test last year was x is greater, or no. Did they? Y is greater than -3. Yeah, interval notation makes so much more sense, so I apologize. Okay, what is the domain and range of f inverse of x? So looking at the blue graph, what's the domain? Oh, Landon he's too smart. Well, if here we switched all of the x's into y's and all of the y's into x's, it only makes sense that the range of f of x will have the same numerical values as the domain of f inverse of x. So I should just be able to switch these. So the range should be -3 to infinity, which on the graph it is. Everything from -3 over. Oh, the domain is bracketed. Thank you. And then the domain, or the... Okay, there we go. Domain, -3 to infinity. Range is all real numbers. The only trouble you might run into there, if you're using inequality notation, you have to make sure that you turn the y into an x. So this would be x is greater than or equal to -3. And technically, you're supposed to, on interval notation, write x equals bracket -3 infinity, but we just leave that off because we're smart. But I mean, I don't think they have interval notation on the ACT. Have you ever seen that? I don't know. You'll take it in a month or so. Then you'll know. Okay. We're going to do the same thing with logarithms now. So, let's take a look at g of x equals log base 4 of x. You need to graph that, but I don't have a log base 4 button. Well, some of you do, but it's a waste of time to find it. So how do we plug in log base 4 of x? We do the change of base formula. So we'll write ln x divided by the ln of 4. Not log, that won't work. ln of 4. Graph that. And let's change your window from -6 to 6 and -6 to 6. It'll be a little bit easier to see everything that way. Yes, just change your window to match mine. So the graph of that looks like this. Something like that. Okay. Well, let's calculate the inverse. Y equals log base 4 of x. To invert, we switch x and y. So x equals log base 4 of y, but now it's in the wrong graphing form. So how do we solve for y? We convert it to exponent. So exponential would be 4 to the x equals y. Now graph that on your calculator on the same screen. So go down to y2 and graph 4 to the x. Do they look like inverses? They do. And actually, it's going to be helpful today if you put that line there, because some of them are not as easy to see as that. So go down to y3 and just graph y equals x. And that will place the 45-degree line on your graph. And you can see they are perfect mirror images of each other. So what is the domain and range for g of x? So domain would be, so on this blue graph that I've drawn, 0 to infinity. Do we include 0? No, it doesn't ever get there. And we never include infinity. What's the range? So negative infinity to, it's actually going to go all the way to infinity. It's not going to get there very quickly, but it will eventually get there. And the way that you can tell, so if we look at this and we say, well, it's leveling off, is it ever actually going to reach infinity? And the question is, if we look at, so if we look at this, log base 4 of x, would that ever equal, say, 1,000,000? So if you had 1,000,000 here, is 4 to what power is 1,000,000? Does that number exist? Yes. What about 1,000,000,000? 4 to what power is 1,000,000,000? It exists, right? And no matter, as your numbers keep getting bigger, your answers keep getting a little bit bigger. So it will never actually level out, and there are some graphs that do, but they're much more complicated than anything you see in high school. So the range here is all real numbers. So if I graph the inverse, we now know that the domain and range are simply inverses of each other. So the domain of this is all real, and the range is going to be from 0 to infinity. And it's worth pointing out, here's an exponential equation. Y equals 4 to the x. Can you pick an x value that yields a negative y value? There is no way for 4 to the x to create an x value that equals a negative number. This graph is always above the x-axis. You cannot make negative numbers using exponents. Likewise, can you plug negative numbers into logarithms? No, for the same reason. No matter what number you create, no matter what number you use, you can never create a negative x value in that case. Okay, so look at number 1. For your assignment today, you need to invert and graph both and verify that they are inverses. So there's no answer sheet on this, but you don't really need one, because if you graph the first one and then you graph the inverse, you'll notice that they're that they are in fact inverses. So first I need to calculate the inverse. Y equals 1.2 to the x equals 1.2 to the y. How do I solve for y? Convert. So log base 1.2 of x equals y. So I'm going to graph them both at the same time. So 1.2 raised to the x. And then I don't have log base 1.2, so I need to use the change of base formula. ln x divided by the ln of 1.2. And I'm going to leave y3 as x. So my original graph looks like this. My other graph looks like this, and they intersect along that line. And eventually they're going to intersect again, right? If we were to go further out in time, they would actually intersect twice. That's easy enough, right? All right, number 2. First I need to invert. X equals e to the y. Now I convert to exponent, or sorry, convert from exponent to logarithm. Log base e of x is y, and some of you noticed log base e is the ln of x equals y. So in that case, it's nice because we have the button ln. There are two e's on your calculator. One of them, if all you want is the value of e, above the delete key is a blue e, but that's not the one that I would use. Above the ln is an e to the x button. And since we are doing e raised to a power, that's what I would push. So push the e to the x button, and then you have to plug x in. And then down here, because we're using base e, it's just ln x. And you'll see that these two do not intersect. That's what those look like. Okay? All right. Wrong button. All right, number 3. So first we need to invert x equals log base 1.5 of y. Now I convert to exponent. 1.5 to the x equals y. And then on this one, I don't have log base 1.5. So ln 1.5 divided by, ln x divided by the ln of 1.5. I messed up something. Oh. Raised to the x. Those almost intersect, but not quite. Oops. All right, one more. So first we invert x equals log base 0.67 of y. What would that be in exponential form? 0.67 to the x equals y. So 0.67 there. And ln of x over ln of 0.67. And these are going to intersect, because they're kind of traveling in different directions. So my first graph looks like that. Second graph looks like that. Are those two inverses of each other? Yes, they are. Okay. You should get this done pretty quickly. I think you'll get it done by the end of class. So good luck.